Right, so trusses are, have fairly straightforward analysis. There's other things that are used called frames and machines that have more complex analyses. Okay, so what I have up there is a whole bunch of different frames and machines. Frames and machines are joined together out of members like trusses are, but they can be joined together in more complex ways. They can also be loaded in places other than the joints. Okay, so frames and machines are kind of a more complex version of trusses. Frames don't move and they support a static load. So that bike rack there is a frame. Machines move and they exert a force or move a load, like a pair of vice grips is a good example of a machine. Okay, so they're analyzed in a similar way, so they're grouped together even though they're different in what they do. Okay, so frames and machines are like trusses, except that they can have what we call multi-force members, which are forces applied where you have more than two applied forces. Okay, so generally speaking, when you have more than two forces applied to these members, the force doesn't act along the axis of the member as it does in a truss. So that leads to a more complicated analysis that you have to do. Now, there's a couple of things to understand about these to kind of start with. So let's start with some of the kind of basic assumptions you make with these. Okay. Now, with a frame and machine, here's a simple one. So I've got this hatched surface here on my page 560. I've got something welded or attached to that surface, and I've got a second object that's pinned on, okay? Like that. If I pull on that with 30 newtons, here's what's going to happen if that thing's in equilibrium. The member itself will be in equilibrium. So that AB will have 30, the original force of 30 to the left, and it will have a reaction of 30 to the right. Now that's exerted by the pin that goes through B. Now the pin will have the pull, or this force from AB, but and to keep the pin in equilibrium, BC will also pull from the other side, and those will be equal and opposite. Okay. Now what the pin does then to BC is it pulls B to the left, so the wall will pull C to the right. Okay. So all of those different pieces are going to feel that 30 newtons. It kind of works its way from AB to the pin to BC. All right. So we're going to kind of work our way through that. Now, as it turns out, you can pretty much just skip over the pins, because if you got 30 newtons to the right at B, you'll get 30 newtons to the left at B on BC. So if AB has 30 newtons to the right at B, BC will have 30 newtons to the left. So we kind of skip over the pins. Okay. Now, what force would you design the pin for? Okay. What do we have going on at the pin? We have the pin in equilibrium. So we have 30, which I would call the applied force. It's going to react with 30 going the other way to hold equilibrium. So that is what's called the reaction. Okay. So the pin has 30 newtons on it. You don't double it up and say 60, it's 30. An action and a reaction. Okay, so that's one thing. As you analyze these, you can kind of skip your way over the pins. And if you got on AB, if you got 30 to the right at B, on BC, you got 30 to the left. All right, now pulleys we get into with these frames and machines sometimes. So if I've got this pulley and a 200 Newton weight, when I cut that free body diagram of the pulley, I'm going to have those forces will both be 200 Newtons, right? And they'll both be pulling forces like that. Well, what the pin's going to do is push back with the opposite forces. So the pin will do that. So the pulley itself will pull down on the frame with those two forces again, 200 newtons each. Okay? So when you analyze the frame, you can go right to where the pin is at and apply those cable forces at the pin. You can move them both to the pin. Because what's happening here, if you don't do that, you're going to get into some complicated dimensioning to figure out where those forces are applied, especially when those cables are at angles. You might have to do some dimensioning like that, and that can get a little messy. So typically what we do is just put the forces right on the pin. Okay. So you take the two cable forces, which are going to be equal. They don't cause any moment because they're balanced about the pulley. You just take them and you tack them right at the pin, at the center of the pulley, and put them on the frame that holds the pulley up. Okay. All right, so that's a couple of things with frames and machines. The last thing here is you can't make this axial assumption anymore. Okay, so if this is a frame, ACG is not a two-force member. The force does not go from A towards G. Okay, so RAY is not equal to FACG times the sine of the angle. It doesn't work that way anymore. It's not that simple anymore. We have to do a little bit more analysis to get to some of these forces. We can't assume that they're two-force members anymore. Okay. So why don't we look at an example here? Now, when we're looking at frames and machines, what we do, we create exploded views of them. We break them up into pieces, okay, and analyze them in that fashion. Before I kind of jump into them, I like to look at them and see if I can find any two-force members. You see any two-force members on this bucket here? This excavator? Yeah. See those hydraulic cylinders? Yeah, those are two-force members because they got a pin there and a pin there. So that's a two-force member there. So we want to identify these things because they're simpler to analyze than the normal members we deal with. So we want to for sure identify these things if we can find them. Okay. So let's have a look at a simple frame here on page 570, see what we can do with it. Let's find the forces in the joints, A, B, C, D, E, and F. Okay, we got a couple cantilever type reactions, so I don't think reactions is going to help us here too much. It's with frames and machines, I often go right into an exploded view. Now, the first thing I want to do on a frame and machine, though, is identify any two-force members. So what I'm looking for is a member with two forces and only two forces, two pins, and that's it. So do you see any two-force members on this one? There you go, BD, yeah. There's two pins, no applied force in between. AD? Oh, but that's one piece. EADF is one thing. So yeah, you're not seeing a break line in there to indicate it's two pieces. It's one. Okay. All right.
Would EA be one? AC.
Well, but AC has B in there.
Oh, okay.
So I think we found them all. BD's pretty much it. Okay. Yeah. I think engineers need a switch. We can just turn off the analysis sometimes. It'd be to our benefit. It's just hard to do. All right, now BD, is that in tension or compression, do you think?
Probably compression.
Yeah, and I think that's a good way to state it. Probably compression, because what's happening there, if you take a moment about A, C's trying to swing counterclockwise, BD has to prevent that. So to prevent it, it's probably going to be a compression. Okay. Now, I'm going to do an exploded view, and when I do that, I represent two force members as just a force. I'm not going to analyze BD, I'm just going to treat it like a force. So that's how I come up with that exploded view down below. So by breaking it up into pieces, you can simplify things a bit and be able to work through the pieces. Okay. So I got A, B, C, and then I've got whatever that is, E, A, D, F. I've got lines on there for forces. So what I would do is I would treat this, I'm going to start over here because this one's got so many forces, I don't think I can do much with it just yet. I'm going to start on the left there because I see 1, 2, 3 unknowns, and I can solve that with statics, see? And where would you take a moment about to start, do you think? Yeah, for two reasons. One is there's a pin joint with 2 unknowns. The other reason is the instructor put a red dot on there already, and that's probably a good tip-off. We're going to take moments about it. Okay, so there we go. So we got 2 of the unknowns there, so we can solve for BD by taking moments, right? So there we go. Sum of MA is 0. I've got 3,000 newtons times 25 and 50 centimeters makes 75 centimeters. So a vertical force of 3,000, horizontal distance of 75 centimeters, 0.75 meters. And then I've got 48 centimeters down to BD, which is going back the other way. That's negative. So I can work through that and find BD. It's 4688. So it's just like a statics problem. See, a lot of this stuff, we're just applying what we learned in equilibrium. We're just doing it in different situations. You know, we did it to trusses. Now we're going to do it to frames and machines. Before we do it to frames and machines, we got to pull them apart into pieces is what we got to do. Okay. So that gets me that 2 force BD. That came out to be positive, so it's 4688 like that. Now I still got 2 unknowns there. I've got AX and AY, but there's 2 of them, and then one of them's in the X, the other one's in the Y, so that should be pretty straightforward to find those with sum of FX and sum of FY, okay? So my next thing to do would just be force equations. Okay. So sum of FX is 0, so FAX is 4688 to the right. Sum of FY is 0, so FAY is 3,000 up. So once I've done that, now I know all the forces acting on this. So one of the important things about these frames and machines is you pull them apart into exploded views. The other important thing about frames and machines is when you go from one member to the other, you turn the forces around. Okay, so if AX is to the right on ABC, it's to the left on this side. And if AY is up on ABC, it's down on the other member, okay? So we got to turn the forces around when we go from one member to the other. If BD is pushing to the left on ABC, it's pushing to the right on this one. So we got to just remember to turn everything around.
Equal and opposite reaction. Things pushing on another thing, the other thing pushing back.
Yeah, pretty much, right, equal and opposite. So as you go from one to the other, we're kind of going from what EADF does to ABC to what ABC does to EADF. So we turn the forces around. So what we've done there is we've used the ABC there. We found those forces, we turn them around and put them on the other piece. They're knowns now. We've only got 3 unknowns left. So we go ahead and work through the other one now, see? So the strategy on these frames and machines is to kind of work your way through, find some of the forces, and then apply them on one member, apply them on the other, turn them around and apply them on the other. And you can kind of work your way through a frame like that. You do have to remember to turn the forces around. All right, so if I've got this on that EADF, now I can go ahead and take a moment about E and solve for FFH. It's 2446 to the right. And once I've got that, I can go sum of FX and sum of FY and solve it out. And then once we've got FH, we can just go sum of Fy equals 0, and that will be what? That will be negative 3,000 plus Fey. That'll get us Fey, it's 3,000 up. And then we can go sum of Fx and set that equal to 0. And what do we got then? We've got 2446 negative. And then we've got 4688. Is that negative 2? I don't know if that's quite what I want there, but is that, you get that right? Yeah, I think so. And then plus Fex. At least I think that's what we got. Did I bust something on that? Yeah, I busted something on that. Oh, I forgot the other 4866. There we go. Okay. Okay. I knew something didn't look right there. So I get Fex, and that is 2446. Okay. So what we're illustrating there is 1, look for the 1, draw an exploded view, 2, identify any 2 force members, start on an easy piece, figure it out, take the forces and turn them around and put them onto the piece it's connected to, and you can work through frames that way. Okay. So we doing all right with that? I want to do a few of these for, I guess it'd be for Monday, wouldn't it? So what the deal is, these are the last 3 that relate to the test. So these will be due Monday. I'll get them back to you Wednesday so you have them. Is that the second, I think? 311, 312,
Second, yes.
313, okay? A couple of those are kind of tricky, but, you know, we'll go over them on Friday if you got questions on them.
11, 12, 13.
Yes. Good to go? All right. Call it good?